All right, today we're jumping into one of the absolute biggest stories in all of science, the epic quest to figure out what everything is really made of. And let me tell you, it's a revolutionary journey that didn't just change our view of reality once, it completely flipped it on its head, again and again.
So, this is the big one, right? What is everything really made of? For literally centuries, the sharpest minds on the planet, from philosophers to scientists, have been chasing after the ultimate building blocks of the universe. And it turns out, the answer to this one question sparked a revolution that, well, powers the entire world you and I live in today.
Okay, so our story really gets going in the early 1800s. This is when we get the first real, testable scientific theory of the atom.
So this English chemist, John Dalton, comes along and proposes that everything is made of these tiny, solid, unbreakable little spheres. You can kind of think of them like microscopic billiard balls. And this idea was a total game changer. It wasn't just some abstract philosophical thought. For the first time, it gave chemists an actual toolkit to precisely measure and engineer chemical reactions.
What's just wild when you look at this timeline is the sheer speed of it all. See, Dalton's idea, that simple little sphere, it held up for almost 100 years. But then bam, in just a little over 30 years, our whole picture of the atom gets completely torn down and rebuilt 4 more times. So yeah, this is going to be our roadmap for this incredible ride.
The first major crack in Dalton's perfect little sphere shows up right at the end of the 19th century. That unbreakable atom, well, it was about to get broken.
A physicist named J.J. Thomson, while messing around with these things called cathode ray tubes, finds a particle that's way, way smaller than any known atom. He discovers the electron. To make sense of this, he comes up with what we now call the plum pudding model. Just picture a ball of positively charged pudding, and stuck inside are these little negative electrons, kind of like raisins.
Now, this was way more than just a new doodle of an atom. By finding the electron, Thomson proved atoms weren't unbreakable after all. But what he didn't know at the time was that he was laying the foundation for, well, everything. Vacuum tubes, old-school TVs, the entire field of electronics, it all starts right here.
Naturally, this new model raises a new question. If atoms are really these soft, mushy puddings, what happens if you shoot something at them? Another scientist, Ernest Rutherford, decided to find out, and his experiment would become one of the most legendary in the history of physics.
So here's the setup. He's going to fire these tiny little positively charged things called alpha particles at a super thin sheet of gold foil. Now, according to the plum pudding idea, these particles should just zip right through the soft gold atoms. Maybe they'd get nudged a tiny bit, but they should basically go straight through.
But that is not what happened. I mean, yeah, most of them went straight through, but every once in a while, like 1 in every 8,000, a particle would come screaming right back at him. The result was just so bizarre, so completely unexpected, that Rutherford's own words capture the shock perfectly. It was, as he said, like firing a cannonball at a piece of tissue paper and having it bounce back and hit you. Just wow.
There was only one possible explanation, and it meant throwing out the old model completely. That positive pudding couldn't be soft and spread out. It had to be packed into an impossibly small, incredibly dense point at the center, what we now call the nucleus. And that meant the atom wasn't a solid thing at all. It was mostly empty space. So this new nuclear model paints a totally different picture. It's like a tiny little solar system with electrons orbiting this dense nucleus in the middle. And just like before, this wasn't just a theory. This discovery was the birth of nuclear physics, which would eventually give us everything from nuclear power to modern medical imaging.
But hang on. Rutherford's model had a big problem. Based on the physics everyone knew at the time, an orbiting electron should be losing energy, right? It should spiral down and crash into the nucleus in less than a second. Atoms should just collapse. This is where a young physicist, Niels Bohr, stepped in with an idea that was as weird as it was brilliant.
Bohr basically said, what if the rules of physics are just different down here at the atomic level? He suggested that electrons can't just orbit wherever they want. No, they're stuck on specific tracks or energy levels. Think of it like lanes on a highway. They can jump from one lane to another, but they can never, ever be in between the lanes. And here's the cool part. These energy levels weren't just random. Bohr figured out that they followed a really simple, elegant mathematical rule. And this rule perfectly explains something that had puzzled scientists for years, why different atoms glow at very specific colors of light. This was the first quantum rule ever applied to the atom, and it was a huge sign that a completely new kind of physics was just around the corner. Now, Bohr's model was revolutionary, for sure, but it was kind of a patch. The final leap, the one into true quantum mechanics, was about to blow the whole idea of neat little orbits right out of the water. It replaced it with something way weirder, but also way more powerful.
Okay, so in the 1920s, physicists like Schrödinger and Heisenberg have a mind-bending realization. An electron isn't just a tiny ball, it's also a wave. And if it's a wave, you can't really say it's in a specific spot. So the whole idea of a fixed path, an orbit, just doesn't make sense anymore. It gets replaced by something called an orbital, which is basically a 3D cloud of probability. It doesn't tell you where the electron is, it tells you where you're most likely to find it.
And that brings us to where we are today. The modern atom has a nucleus made of protons and neutrons, and it's surrounded by these blurry, fuzzy clouds of electron probability. Thanks to the Heisenberg uncertainty principle, you can never know exactly where an electron is and where it's going at the same time. Its whole life is run by a set of quantum rules, which are basically like its unique address inside the atom.
So, you might be thinking, okay, that's a pretty wild ride from simple billiard balls to weird probability clouds. But why should I care? Well, here's why. That final, bizarre, quantum model of the atom, it's the foundation for pretty much every single piece of modern technology you touch. You see those weird quantum rules about electron orbitals and energy levels? That's what makes semiconductors possible. If we hadn't figured that out, we wouldn't have transistors. And without transistors, no computer chips, no smartphones, no internet. The whole digital world we live in is built on this strange quantum physics. And it goes way beyond computers. Understanding the atom lets us design and build materials with incredible properties. Everything from super strong metals for jets to plastics that can conduct electricity. And remember that nucleus Rutherford found? Well, knowing how that works gives us nuclear power plants and the MRI machines that let doctors see inside us without ever making a cut.
And the story is far from over. Right now, scientists are literally moving individual atoms around to create amazing new things like graphene and quantum dots. Those quantum leaps that Bohr talked about, that's exactly how lasers work. And all those bizarre rules of probability, we're now using them to try and build the next generation of computers, quantum computers.
When you step back, it's just an incredible story. In a little over 100 years, we went from seeing the atom as this simple, solid, unbreakable ball to seeing it as a buzzing, dynamic cloud of pure possibility.
It just goes to show you, right? The more we learn, the more we realize we don't know. It really makes you wonder, our current model of the atom literally built the modern world. So what other secrets is it hiding? What comes next?